Welcome to the Complete Guide to Derivatives. This video is a compilation of all of my derivative lessons on this channel. This video will cover all of these subjects, and timestamps will be placed throughout the video in case you want to find one specific subject. The original videos will also be linked with info cards in the top right corner. Enjoy the video. In today's video, we're going to be introducing derivatives in Calculus 1. We're going to be going over what derivatives are, what they look like on a graph, and how to solve and find derivatives of any equation. So let's get started. First of all, let's define what a derivative is. A derivative is an equation that we can find from an original equation that gives us the instantaneous rate of change at any point along a graph. So if I were to have a graph and I had an equation for that graph and I were to take the derivative and find the derivative of that graph, I could plug in whatever my point is to my new derived equation and find how that function changes at a given point. This is known as the instantaneous rate of change, and the line that is created at that specific point is known as the tangent line. To help you visualize what a derivative looks like, I'm going to use this graph. This graph doesn't have an equation, but we can use it to figure out what derivatives look like once we solve for them. So at this point, we want to find the instantaneous rate of change, just at that point. So the tangent line would look something like this. So the slope of this new tangent line is the instantaneous rate of change at that point on the graph. Same thing can be applied for both of these points. It'll look something like this. Slightly downward and upward in that direction. And then here, our tangent line looks something like this. The slope of these individual lines is the instantaneous rate of change for each of these points along this graph. And we can find an equation that will give us that exact instantaneous rate of change no matter what point we use on the graph. So let's talk about solving them and how derivatives work, because I think it's really important to understand what's actually happening when you find a derivative. I've drawn this graph here, and in order to understand what's going on in this graph, we need to define the equation that can help us find any derivative. That equation is the limit as h approaches 0 of f of x plus h minus f of x divided by h is equal to our derivative, which can be denoted as d dx, or f prime, which is that little apostrophe symbol, x. This equation can find us any derivative of any function. And yeah, it's kind of a mess, but it will solve for any derivative. But what's up with this limit being here? What's actually happening? What do we mean by h approaching 0? You can see that h is defined by the distance between 2 points on a graph. And as we bring these points closer and closer together, we can get something that's closer and closer to the tangent line at a given point. Let's represent that visually because it's a little bit hard to understand with just a still picture. So let's say we decrease the distance between these points to this. This is now h, not what we had before. This distance is h, right here. If we were to draw a line between these 2 points, that's not really very close to our tangent line, but compared to our tangent line from a second ago, which would look something like this, we are definitely closer to the tangent line for the instantaneous rate of change of this slope. So let's move this point even closer to the point we're looking for the tangent line for, say really right next to it, this distance here, h. If we were to draw a line between these 2 points, we are much closer to the instantaneous rate of change at this point down here. And if we were to bring these points right up next to each other and draw a line between them, we would get something like that. So as the distance between 2 points, h, gets closer and closer to 0, we get something that's closer and closer to equaling the tangent line, which is our derivative, aka the tangent line, aka the instantaneous rate of change at any given point. So that's what's actually happening when we use this equation, and that's why we have a limit introduced in this equation in order to solve for tangent lines. But in your classes, you don't have to necessarily explain that, so I think we should try and solve some. Let's solve some basic derivatives together. I'm going to leave this equation up here as a reference so we can use it as we solve these equations, but I'm going to erase this so I have a little more room. Before we begin, I want to re-emphasize something. F prime of x and d dx are the same notation. This just means the derivative with respect to a variable. You'll hear that term with respect a lot as we go through derivatives, so I'll try to make that as clear as possible as we do this. With respect to a variable is more important when you get to multivariable calculus, but basically it means we're finding the derivative for the x variable. When you get into multivariable calculus in calculus 3 and further down the line, we'll take respect to other variables, but for today, don't worry about that. We're not doing any of that anytime soon. So let's use this equation to find a derivative. Let's find the derivative d dx of x squared. What is the derivative of this equation? Well, let's plug in this into our equation that can solve any derivative. So first of all, when we have a function f of x plus h, that means we have to replace every x value with x plus h. F of x is just the function f of x, and h is just h. So let's plug in all of these values into this equation and then plug that into our derivative equation. This can be turned into the limit as h approaches 0 of f of x plus h, which is this equation, but replaced with x plus h instead of just x. So in the numerator, we have x plus h squared. And then here we just have minus f of x, which is just subtracting our function. So that would be minus x squared. And on bottom is just the variable h, which we can see right here. Let's bring this equation up here, so that way we have a little more room to work with. So now we'd have the limit as h approaches 0 of x plus h squared. Now remember, this isn't just x squared plus h squared, this is x plus h times x plus h. Don't forget to do that or else you may get some of these equations wrong. So this is x plus h times x plus h. And that's a very common mistake, don't worry. I just want to point that out in case you didn't realize it. And of course, we just have to add this minus x squared over here and divide that by h. Let's actually multiply these together and FOIL them out. So now we have the limit as h approaches 0 of x squared plus hx plus hx plus h squared minus x squared. And that's all still divided by h. You may notice that we have a few factors that we can combine. First of all, x squared minus x squared is just 0, so we can cancel those out. And hx plus hx can be combined to be 2hx. So this equation is now the limit as h approaches 0 of 2hx plus h squared divided by h. And you may remember when we were solving limit problems, sometimes we can just plug in whatever our variable is approaching to our equation to solve for the limit. But the problem here, of course, is that with just the h on bottom, we would end up dividing by 0. So let's try and cancel something out. There is one thing that we can do to this equation to make it much easier to solve. And what I'm going to do is I'm going to factor out an h. Both this and this have an h that can be factored out. Let me show you what that looks like. So this will now turn into the limit as h approaches 0 of h, I factored in h out, times 2x plus h. So what I did here was I pulled an h out of both of these. If we were to multiply the h by both these variables, we get 2hx plus h squared. We just pulled it out. We didn't change the value of it at all. And we're still dividing by h on the bottom. Now you'll see that this h and this h will cancel out to just equal 1. So now our limit as h approaches 0 is 2x plus h. And now we don't have to worry about dividing by 0 or anything. We can just plug in h right here. Of course, that's equal to 0, so this derivative is just equal to 2x. That is the derivative of x squared. Now, I know this looks like a lot because this equation, to be honest, is a pain in the butt. But in future videos, we'll talk about how to solve these equations much more easily, especially something like x squared, which is actually very easy to solve without this massive equation. But let's do one more example with this equation so you get the hang of it. You will have to use it every now and then. I also moved our derivative definition up here so that way I have a little more room to work. Let's find the derivative of the square root of 2x plus 3. We're going to plug this into our derivative definition, and I know this is going to take quite a while to solve, but bear with me, it'll help us understand how these derivatives work. So let's just start by plugging everything into here. First of all, once again, we have to replace every x within our function with x plus h. So this now turns into the limit as h approaches 0 of the square root of 2 times x plus h plus 3 minus f of x, which is just our function, the square root of 2x plus 3. And once again, this is all just divided by h. Now, it may look like we're kind of stuck here, but we can use a strategy that we learned about in limits to help solve this problem. You may remember a video where I talked about solving limits by rationalizing, and I'll link it here if you don't. What we can do is we can multiply this function by the conjugate in order to solve this equation. If you don't remember what the conjugate is, let's say we had something like square root of 2 plus 7. The conjugate of this equation would just be the square root of 2 minus 7. The conjugate of something is just replacing this middle sign with the opposite sign. So if we have addition, we replace it with subtraction, and if we have subtraction, we replace it with addition. We're going to use that concept here to multiply this whole equation by 1. I'll show you what I mean by that. We're going to multiply this by the conjugate of the top. So we're going to multiply this by 2 times x plus h plus 3 plus 2x plus 3. And we're also going to multiply the bottom by that same value, the square root of 2 times x plus h plus 3 plus the square root of 2x plus 3. And you'll notice, since I'm multiplying it by a fraction with the same thing on top and bottom, it's essentially the same thing as multiplying by 1. If we were to divide the top by bottom, we would just get 1, so we're not actually changing the value of this equation. On the top, we just need to FOIL everything out. The square root of 2 times x plus h plus 3 times itself will just be the same thing, but without the square root. So we're going to need some room, so let's rewrite everything down here. Limit as h approaches 0. On top, we now have 2 times x plus h plus 3, and we're just going to extend this way out here. We're going to need a lot of room to solve this. Next, we multiply this by the square root of 2x plus 3, and that is just equal to the square root of 2 times x plus h plus 3 times 2x plus 3. They're all under the square root, so we can just put both equations under the square root like that. Now let's FOIL from here. We now have minus this exact same value, minus the square root of 2 times x plus h plus 3 times 2x plus 3, like so. And then our last thing to FOIL out is the square root of 2x plus 3 times the square root of 2x plus 3, which is just equal to 2x plus 3. On bottom, we just have to multiply this by h. So let's do that. This is just h times the square root of 2 times x plus h plus 3 plus the square root of 2x plus 3. And yes, that was a lot to do. But fortunately for us, we can cancel out a couple things. First of all, this plus and minus of the same thing will cancel out. Bada bing, bada boom, that's all gone now. So we can now rewrite this equation as the limits as h approaches 0 of, and let's FOIL this one out because it's simple, 2x plus 2h plus 3, that's what this is. Oh, actually I made a mistake here because if you multiply this negative version and this positive version together, we will remove the square root, but this will be a negative sign. Sorry about that. This is now minus 2x and also minus 3. So now we just bring this down as minus 2x minus 3. Sorry for the confusion, just want to make sure we get that right. On the bottom, we have the same thing. That's just h times the square root of 2 times x plus h plus 3 plus the square root of 2x plus 3. Now we got something a little bit simpler. First of all, our positive 2x and our negative 2x will cancel out, and our 3 and negative 3 will also cancel out. Isn't that convenient? So now this equation is just equal to the limit as h approaches 0 of on top is just 2h, I know, very convenient, divided by h times the square root of 2 times x plus h plus 3 plus the square root of 2x plus 3. Now we're really getting somewhere. And in fact, we have one more thing we can cancel out. We can cancel out this h and this h. So now this is equal to the limit as h approaches 0. And if I go off camera, it's so that way you can see the board because there's a lot here and I don't want to block any of it, is now equal to 2 divided by the square root of 2. The square root of 2 times x plus h plus 3 plus the square root of 2x plus 3. We are almost there for solving this derivative, but we just have a little bit more to do. We are now at the stage where we can plug in 0 for h. So this is now just equal to, instead of h, 0. Instead of rewriting it all, I'm sure you can figure out that h is replaced with a 0. Of course, this 0 doesn't actually change anything on bottom, so now we have the square root of 2 times x plus 3 plus another square root of 2x plus 3. So just to rewrite that and make that very clear, this is equal to the limit as h approaches 0, 2 divided by square root of 2x plus 3 plus the square root of 2x plus 3. Sorry, that's not supposed to be a parenthesis. That's supposed to look like that and that. And since we have two of them, this equation can actually turn into, oh, forgive me, we actually don't need to write this h approaches 0 part anymore because we already plugged in h. So we don't need this anymore. Sorry about that. This is now equal to just 2 divided by 2 times 2x plus 3. And once again, we can cancel these two out. So our final equation and the derivative of square root of 2x plus 3 is equal to 1 divided by the square root of 2x plus 3. And this is our derivative. Now, I know that seems like a lot, and trust me, even for me, as someone who's done this before, this is a lot of writing to do, and fortunately we have shortcuts that can help us solve these derivatives much faster. We'll get into that in future videos like I said before, but like I said, I want you to know how much of a pain in the butt this is so that way you really know your shortcuts, so you don't have to use this equation very often. So that's the last we're going to talk about these equations, but I do want to talk about places where the derivative may not exist. Just like in limits, there's places where we can't derive a function. Sure does feel nice to have a clean slate now. Let's talk about where derivatives may not exist. I'm going to draw 3 graphs here. And the functions attached to this graph won't be defined. We don't need to define them, I just need to show you the concept. So we have 3 different xy planes here. It looks something like that. This first graph looks something like this. It's just some sort of upward curve, but bang, there's a hole right there. And it goes on forever and ever from negative infinity to infinity. But if we were to try to find the tangent line at this hole specifically, we couldn't. We cannot find derivatives at holes or discontinuities. Now we could find the derivative at some other point along this line, like let's just say here. We could find the derivative, the tangent line right there. We could find that. That's no big deal. But specifically at holes, we can't because, well, the function doesn't exist there. Let's draw another function that looks oddly similar to this one, but it has a hole right there and also has a point down here. This is known as a removable point because it's within the same plane and we could put it there to make the function continuous, but it has been, well, removed. We can also not find the derivative at this point here. But why? Why can't we find this derivative? It is a continuous point at this very point, right? Well, the big problem is we don't actually know what this tangent line is supposed to look like. We don't know what direction it goes in. We don't know the slope. We don't know anything about it. It could be infinitely many of these lines. I'm just going to draw a bunch of them to give you an idea that technically this tangent line could be any of those. And since we have no idea which one it should be, there is no derivative at this point. If we have infinitely many options, then we have no options. And the last example I'm going to talk about is, well, I've used this example quite a few times in the past couple of lectures. This equation is y equals 1 divided by x. As you may be able to tell, we can't plug in 0 on bottom for x because then we get 1 divided by 0, which does not exist. So we have this big old vertical asymptote here. Now this function does have a derivative. It can be solved, it does have a derivative, but we cannot find the tangent line at this vertical asymptote. We have an infinite discontinuity at x equals 0. So we cannot find a tangent line, aka the derivative, aka the instantaneous rate of change, at this point. We can find it anywhere along these 2 lines, but not at 0. It is what it is. In my last video, we talked about derivatives, what they are, and how to solve them. In this video, we're going to make it much easier to solve derivatives. Because in my last video, we solved derivatives using the equation for derivatives, which is the limit as h approaches 0 of f of x plus h minus f of x divided by h. And this equation is long and a pain in the butt. And we have ways that can make it much easier to solve derivatives. So let's talk about those methods that can make derivatives easier to solve. And some of these methods will have their own lessons in the future. When those videos are posted, I'll link them with the info cards up above in the top right corner. Let's get started. Our first rule is the constant rule. The constant rule states that the derivative, d dx, of a constant, let's just say c for any constant, is just equal to 0. If you have a constant number, the derivative is always equal to 0. But why is it always equal to 0? Well, let's say we have a graph. We're going to draw that graph over here. And let's say we have a function. We'll do this in red. And our constant function looks like this. And this is at y equals 4. Remember, when we solve for derivatives, the entire point of finding the derivative equation is to find the instantaneous rate of change of a graph at a given point. And this graph doesn't change at any given point. So the derivative equation is always just 0 since nothing ever changes. As a quick example, the derivative, d over dx, of 7 is just equal to 0. This one's a pretty simple one to understand, but very, very important to remember. Next up, we got the power rule, and this is one of the rules that will have their own video, and that video will be linked up in the top right. The power rule is as follows. The derivative, d over dx, of some variable, we'll use x, to a power n is equal to n times x to the n minus 1 power. So what we do is we take our original power and we bring it to the front. And then we subtract 1 from this power to get our derivative. In my last video, we did the example of the derivative of x squared, and that took absolutely forever to solve. Now we can make this really easy. First, we want to bring this 2 to the front. So it would be 2 times x, and then our new exponent we just subtract 1 from. So we take the old exponent, which is 2 minus 1, which is just equal to 2x to the first power. Anything to the first power is just whatever the original number was. So x to the first power is still just x, therefore we don't need to write that power, it's just 2x. So that's the power rule. Like I said, I'm going to do another video on this more in depth because there's a lot of ways we can use the power rule that you may not think of off the top of your head. The third rule is actually 2 rules, but they're basically the same thing, is the sum and difference rule. So the sum and difference rule states that the derivative, d over dx, of f of x, or whatever variable is in here, plus another function, g of x, just 2 different functions being added together, is the same thing as the derivative, d over dx, of f of x, plus the derivative of g of x, the other function. In other words, we can split any derivative by addition. And you may notice I also wrote difference here. We can also do this for subtraction, so I'm just going to write it here. We can split any derivative by addition and subtraction and still get the same answer. In other words, we can solve for each derivative individually first and then just add or subtract them to combine it to find our derivative of our original equation. Let's do a quick example, and let's do it in red just for fun. Our example here will be the derivative of x squared plus 3. We can split this into the derivative d dx of x squared plus the derivative d over dx of 3. Using our power rule, the derivative of x squared turns into 2x, and using our constant rule, the derivative of 3 is just 0, so this derivative is just 2x. And we could do the same thing for subtraction, just replacing with this plus with a minus. Now rule number 4 and 5 are a bit longer, so I'm going to erase this to give myself plenty of room to work with. Rule number 4 is the product rule. Similarly to the sum and difference rule, we have a special rule for finding 2 functions being multiplied together and using that to find the derivative. But this one's a lot different than the sum and difference rule, and that's why it gets its own category. You see, the product rule isn't as simple as the sum and difference rule where we can just find the derivatives and then multiply them by each other. This one has its own special equation. If we want to find the derivative of f of x, one function, times g of x, another function, we have to do this. This is equal to f prime of x times g of x. Remember, f prime is just the derivative of f of x plus f of x times g prime of x. So the derivative of our second function. So all we have to do is find the derivative of f of x and g of x and then multiply it by its correspondent to find our new derivative. Let's do a quick example. And we'll use red once again just for fun. So our example will be 3x squared times 7x. What is the derivative of this function? Well, let's use our product rule. So first let's establish what f and g of x are. F of x will be 3x squared, it's just the first one. And g of x will be 7x, and this is g of x. So using that, let's find f prime of x, in other words, the derivative of f of x. We'll do it up here in this corner because we have the room. So the derivative of 3x squared can simply be solved by using the power rule. We can pull this 2 to the front, so this would then turn to 3 times 2, multiplied by x to the 2 minus 1 power. Remember our power rule, we just bring whatever our power is to the front, multiply by whatever's in front, and then subtract 1 from the exponent. This is now equal to 6x. So f prime of x is 6x. So let's plug that in over here. So it'll be 6x times g of x, which is just 7x. Now we have to add f of x times g prime of x. We already know what f of x is. That's just 3x squared. And let's find g prime of x. We'll do that over here in this corner because I don't have room here. So to find g prime of x, we actually need to use the power rule, which may sound weird because there's not a power here, but let me show you what happens here. If we want to find the derivative of 7x, there is a power here of 1. We just don't write it because we don't need to show it. So what happens is we pull down this 1 to the front. So this is equal to 7 times 1, which doesn't really change anything, times x to the 1 minus 1 power. This puts our x variable to the 0th power, and anything to the 0th power is just 1. 7 times 1, of course, is just 1, so the derivative of 7x is just 7. So we just multiply 3x squared by 7. And now it's just a matter of multiplying everything together and adding them. 6 times 7 is 42, and x times x is x squared. So the first part is just 42x squared. 7 times 3 is 21, and we just have an x squared. So this is now equal to 21x squared. And we have a common factor, which means we can just add these two together. 42 plus 21 is equal to 63. So the derivative of 3x squared times 7x is just 63x squared. And I know all this power rule stuff may be a little bit confusing. If you need more details about the power rule, go watch my video on the power rule. This will help clear this up tremendously. There will also be an individual lesson on the product rule, because this is another thing that takes a lot of practice to get used to. So if you'd like to watch that, you can click the info card in the top right corner. We have 2 more properties to go over. Property number 5, let me get my black pen out. Property number 5 is the quotient rule. We use this rule when we are dividing 2 functions, but it also has its own special rule. The derivative of one function, f of x, being divided by another function, g of x, is equal to g of x, this denominator, times f prime of x, the numerator's derivative, minus f of x, the numerator, times g prime of x, the derivative of the denominator, all divided by g of x squared, the denominator squared. So this function is kind of long, but we have to do this in order to find the derivative of 2 functions being divided by each other. Let's do an example to make this a little bit more clear. So our example down here is the derivative 3x divided by 7x squared. So just like with the product rule, let's establish what f and g of x are. F of x will always be your numerator, so in this case 3x is f of x, and g of x will always be your denominator, so 7x squared is our g of x. Now remember, we must keep this order in mind with the quotient rule. With the product rule, you could have flipped these two and it doesn't matter because they're being added. With subtraction, we must do this and then subtract this from that. So let's keep that order in mind. First of all, let's find f prime of x and g prime of x. In other words, the derivatives of f of x and g of x. Similarly to 7x, the derivative of 3x is just 3, using the same rule as before, but with the number 3 instead of 7. So we need to multiply that by g of x. G of x is 7x squared, and that is being multiplied by 3. Now we need to subtract f of x, of course just being 3x, and multiplying that by g prime of x. We can find this derivative using the power rule, so let's do that over here. The derivative of 7x squared using the power rule is equal to 2, bringing down this to the front, bringing down this exponent 2 to the front, times 7, which was our original coefficient, times x, and then subtracting 1 from our exponent, 2 minus 1. So this turns into 14, 2 times 7 is 14, times x to the first power, which we don't need to write. So the derivative of 7x squared is just 14x. So we just multiply 3x by 14x. And on the bottom, we just have g of x squared, which means we just need to square 7x squared. So this is equal to 7x squared squared. Let's multiply these out and combine like terms. 7x squared times 3 is just going to be 7 times 3 and tacking an x squared onto the front. 7 times 3 is just equal to 21. So this is 21x squared. 3 times 14 is equal to 42. X times x is equal to x squared. So we subtract 42x squared. And this is all divided by 7x squared squared. We can combine like terms here. So this is now equal to negative 21x squared divided by 7x squared squared. To square 7x squared, we just need to multiply 7x squared by 7x squared. So this is now equal to negative 21x squared divided by 49x to the fourth. We can actually cancel out these x's on top and bottom. So we get rid of the x squared entirely and change this into x squared. This is now equal to negative 21 divided by 49x squared. And we can divide both the top and bottom by 7. 49 divided by 7 is just 7. Negative 21 divided by 7 is negative 3. So the derivative of 3x divided by 7x squared is just equal to 3, negative 3, divided by 7x squared. Now, I will admit, the quotient rule is not the easiest way to find this derivative, but it is a good example to use just as something basic to understand quotient rule. If you'd like more detail on quotient rule, my quotient rule lesson is linked in the top right. And the last property I want to go over is one I just kind of forgot to mention earlier. Property number 6 is the constant multiple law, or I guess constant multiple rule. And we could have used this to make the quotient rule problem we just did much easier. Essentially what this says is in order to find the derivative of something, let's just say c, a constant multiplied by a variable, we can actually pull this constant out of the derivative. So this would be equal to c times the derivative of our f of x function, which I just wrote as x, but x could be any function. If we have a constant being multiplied by our entire function, we can actually pull it out to the front, then find the derivative of this inside function first, and then multiply it by c. So referring back to what I meant by making the quotient rule problem a little easier, if we have this same example, the example we just did a minute ago, the derivative of 3x divided by 7x squared. You may be thinking there isn't anything being multiplied by the entire function here, and that's where you'd be wrong. This 3/7 is being multiplied by the whole function, and this is a constant that we can pull out. This is now equal to 3/7 times the derivative of x divided by x squared. We can simplify this down a little bit to be 3/7 times the derivative of 1 divided by x. We can cancel out the x on top and get rid of 1x on bottom. So now we just have to find the derivative of 1 divided by x. And in this video, I won't show you how to find this derivative, but I will tell you that this derivative is equal to -1 divided by x squared. And now we can just multiply that by 3/7. So 3/7 times -1 divided by x squared is just equal to -3 divided by 7x squared, which is what we found last time. I'm sorry to put you through that whole quotient rule for a problem that was much easier, but I figured you should know the quotient rule and use it a few times because you will need it for some problems where the quotient rule is absolutely necessary. In today's video, we're going to be talking about the power rule for derivatives. In my intro to derivatives video, I used this equation to solve every single derivative problem, and it's really long and sucks. But fortunately, we have some things such as the power rule that can make derivatives really, really easy to solve. And we're going to talk about arguably the most common one, the power rule, today. The power rule states that if we're trying to find the derivative for any function raised to the n power, so whatever power you have, this is equal to n times x to the n minus 1 power. So what's actually happening is we pull down whatever our original exponent was to the front, and then we subtract 1 from the exponent to find the derivative. And let's do some examples to make this a little bit easier to understand. Our first example will be something pretty simple. We want to find the derivative of x squared. What is this equal to? This function is screaming for us to use power rule. All we have is an x raised to a power, so to find the derivative, we can just use the power rule. Let's apply our power rule to this function. First of all, what we have to do is bring down our 2 to the front, our n value. And then we just need to subtract 1 from 2. So this now turns into 2, which has been brought down to the front, x to the 2 minus 1 power. Of course, this is now equal to 2x to the first power. But remember, anything to the first power is just itself, so we don't even have to write the first power. This is just implied. So the derivative of x squared is just 2x. Let's do some more difficult examples for different situations, because the power rule is a lot more useful than you might think. And of course, the rule will be here in case you ever need it. Example number 2. Let's find the derivative of 8x to the 4th power. What is this derivative? Now, the only real difference between this problem and this problem is that we have a coefficient already. So what do we do there? Well, we still pull down our power to the front. So we're going to put this 4 here, and we still subtract 1 from 4. So what happens when we pull this 4 down to the front? Well, we just multiplied this 4 by our old coefficient 8. So this is now equal to 4 times 8 x to the 4 minus 1 power. Simplifying this down, 4 times 8 is equal to 32 times x, and then 4 minus 1 is just 3. So the derivative of 8x to the 4th is 32x cubed. Pretty simple, right? Not too much harder than the last example. Let's do some examples where you may not think to use the power rule right away. In this example, we have the function square root of x. What is the derivative of this function? Now you may be asking me, hey, Callum, that's not a power. That's a square root. How are we going to apply the power rule to a square root? Well, here's a neat little thing in math that'll actually help you a lot in Calculus 1. The square root of a function, say x like we have here, is the same as x to the 1/2 power. So let's convert our function into x to the 1/2 power. this is equal to d dx of x to the 1/2 power. And now you can see it's pretty easy to apply the power rule. Now we just need to bring down the 1/2 and subtract 1 from it. So this now turns into 1/2 times x to the 1/2 minus 1 power, which is just equal to negative 1/2. So you could leave it in this form and this would be a correct answer, but I'm going to simplify this down a little bit more and we're going to use a little bit of algebra that you may not remember. A negative power will put whatever function you're raising it to in the denominator. So this function can be simplified down into 1 divided by 2x to the 1/2 power. And since the 1/2 power is the same as the square root of x, I just think it looks nicer if we write 1 divided by 2 square root of x. I just think that looks a little nicer. So this is your most simplified answer, but most teachers will still accept this. In this example, we have the function 1 divided by x. What is the derivative of this function? Now, once again, you may be asking, there's no power in this function. How are we going to use the power rule for a function that has no power attached to it? And once again, just like our square root, we actually do have a power attached to it. Remember, just a minute ago, we talked about how negative powers puts whatever you're raising it to in the denominator. So this is actually equivalent to x to the negative first power. That would just put x in the denominator and have it be 1 divided by x. These two are equivalent. Once again, we can easily use the power rule here. Let's bring our negative 1 to the front, as such, and then subtract 1 from it. So this now turns into negative x. We could write a 1 here, but it's not necessary, to the 1 minus 1 power, which is equal to negative 2. And once again, with a negative exponent, we can bring this down to the bottom, and our exponent turns positive. So this answer is negative 1 divided by x squared. And that is the derivative of 1 divided by x. We're going to do one more example in this little space we have here, and that'll be it for this video. The power rule is pretty simple, but extremely helpful. So our last example for this video will be this. We want to find the derivative of 2x. Now you may be saying, hey, that looks pretty simple like some of the ones we did up here, but I want you to notice that we don't have a power here, or it doesn't look like it at least. But once again, there is a power right here. We have a 1 right there. We don't have to write the 1, but there is a 1 there as it's implied. We don't have to write the 1. So let's apply the power rule here. If we bring this 1 down to the front and then subtract 1, we get our new equation, which is 1, hold on, let me write that in green, 1 times 2 x to the 1 minus 1 power, 1 minus 1. Now, as you hopefully know, 1 minus 1, of course, is equal to 0. So this derivative is equal to, and of course 1 times 2 is just 2. This is equal to 2x to the 0th power. So what is the derivative? Well, anything to the 0th power is just equal to 1. And since x is being raised to the 0th power, it's just equal to 1, which means we can cancel out. So the derivative of 2x is just equal to 2. This is a nice little trick to know. If you have any coefficient being multiplied by just x or just y or whatever variable you're using, the derivative is just whatever the coefficient is. And I wanted to show you that with this example. In today's video, we're going to be talking about the product rule for derivatives. This is a strategy that can help us solve problems when we have two functions being multiplied together and we want to find their derivative. The rule is as follows. The derivative of f of x times g of x, in other words, two functions being multiplied by each other, is equal to f prime of x times g of x plus f of x times g prime of x. Now remember, prime is represented by this little apostrophe, and prime is the same thing as the derivative. It's just a shorter version of writing d dx. So let's use this rule to solve some derivatives. It takes a little practice getting used to, but fortunately we have this addition sign, so if you accidentally multiply f of x times g prime of x here instead of f prime of x times g of x, it doesn't really matter because you can flip them and it doesn't change anything. Anyways, let's do the examples now. Example number 1, 3x squared times 7x. And we want to find the derivative of this function. So how might we find the derivative? Well, clearly we have two functions being multiplied by each other. After all, this is the product rule video. So let's first establish what f of x is and what g of x is. And it doesn't really matter too much if you choose one to be f of x and the other to be g of x. As long as one of them is f of x and g of x, it doesn't matter. For me, I'm going to use the first function as f of x, this 3x squared, and our second function, 7x, as g of x. as such. Now we need to find the derivative of each of these functions individually, and we can do that over here in this space. So the derivative of 3x squared, which we'll apply here, can be found using the power rule, which I made a video on recently. You can check it out over there. So let's do that. The derivative, d dx, of 3x squared, if we use the power rule, we bring this 2 to the front and then subtract 1 from our power. So this is equal to 2 times 3x to the 2 minus 1 power, which is just equal to 6x. So now we know what f prime is. We can write it here. Let's write that here. So our f prime is just 6x, and then multiplying that by g of x, which is just 7x. So the first half of our equation is 6x times 7x. Now we have to add f of x times g prime of x. So let's add f of x, which is 3x squared. And now we need to figure out what g prime of x is. And here we have g of x, so let's find the derivative. Once again, in order to find this derivative, we can just use the power rule. The derivative of 7x, remember there's a little invisible 1 here. We can bring that to the front and then subtract 1. So this is equal to 1 times 7x to the 1 minus 1 power, which is 0. X to the 0th power, anything to the 0th power in fact, is just equal to 1. So our derivative is just 7. So we multiply 3x squared by 7. Now that we have everything, we just need to multiply everything together. 6 times 7 is 42, and x times x is equal to x squared. So the first half is 42x squared. Now we have 7 times 3 is 21, and we just tack on the x squared. So this, we also add 21x squared. And since we have a common variable in x squared, we can just add them together. So 42 plus 21 is equal to 63x squared. And that is the derivative we found using the product rule. Let's do 2 more examples for this video. Next we have the example 4x times x plus 7. And you'll notice that this example is slightly different because in the parentheses we have x plus 7 instead of something like 7x or something similar where we have a coefficient attached to x. We can still apply the product rule to this. Let's do that. Once again, let's establish which one's f of x and which one's g of x. I'm going to use this one, f4x, as f of x, and x plus 7 as g of x. Kind of like before, first one is f of x, second one is g of x. You don't have to do it like that, but it just makes more sense to me. So first let's find f prime of x, and I'm going to erase that so we have a little more room to work with. So we need to find the derivative, or f prime, of f of x, which is 4x. So we're just finding the derivative of 4x. Once again, we can just use the power rule. So we bring our invisible 1 here to the front, and then subtract 1. So this derivative is equal to 1 times 4x to the 0th power. Once again, x to the 0th is just 1, so this cancels out. So this derivative is just 4. So the first half of our equation is set. F of x, which is just 4, is being multiplied by g of x, which is x plus 7, as so. And now we need to add f of x times g prime of x. So we already know f of x, that's just 4x over here. Add 4x, and then multiply that by g prime of x. So let's find the derivative of x plus 7. Doing that up here, we get d dx of x plus 7. So we can actually split this between the addition sign, meaning we can solve this derivative and this derivative individually and combine them together to get our final derivative. The derivative of x is just 1, and using the constant rule, the derivative of any constant is just 0, so this derivative is just equal to 1. So this is just 4x times 1. Now we just have to distribute and add everything together, so this is now equal to 4 times x is just 4x, 4 times 7 is just 28, and then 4x times 1 is just 4x. So the derivative of 4x times x plus 7 is just equal to, we can add these two together, 8x plus 28. And that's our derivative. Not too bad, right? Well, let's do one more example that's a little bit trickier. Our last example is 3x minus 1 times x to the 4th plus 2. Let's find the derivative of this. And as you can see, we have two different functions being multiplied by each other. So once again, we do need to apply the product rule. So first, let's establish what f of x and g of x are. Once again, we'll just use the first function as f of x. So 3x minus 1, it will be our f of x. And x to the 4th plus 2 will be our g of x. Now let's use our product rule. First, we need to find f prime of x. In other words, the derivative of f of x. So let's find the derivative of 3x minus 1. In my properties of derivatives video, we talked about the sum and difference rule, and we just did that up here actually, and we can apply that here. We can separate these two by the subtraction sign and solve them individually. The derivative of 3x is just equal to 3. We did a very similar example up here using the power rule, and the derivative of any constant such as -1 is just 0. So the derivative of f of x is just 3. Writing that down here, we get 3 times g of x, which is just x to the 4th plus 2. And now we just need to add f of x, which is 3x minus 1, times g prime of x. And we're going to solve that down here as well. Our g of x function is x to the 4th plus 2. So d dx of x to the 4th plus 2. Once again, we can split this derivative by the addition sign and solve for each of these derivatives individually. So first of all, the derivative of any constant is just 0, so we don't have to worry about that. Using the power rule, we can take that 4 down to the front and subtract 1. So our derivative of x to the 4th plus 2 is just 4x cubed. So let's plug that in up here. So we're multiplying all that by 4x cubed. Okay, that took a second, but now we can pretty easily just FOIL everything out and solve. So let's do that. We can multiply 3 by everything in the parentheses, and we can multiply 4x cubed by everything in these parentheses. So this now turns into 3x to the 4th plus 6, 3 times 2, of course, just being 6. 3x times 4x cubed, 3 times 4 is just 12, x times x cubed is just x to the 4th. So this is plus 12x to the 4th, and then 4x cubed minus 1 is just negative 4x cubed. So simplifying this down, the derivative of 3x minus 1 times x to the 4th plus 2 is equal to 15x to the 4th. We can add 3x to the 4th and 12x to the 4th, minus 4x cubed, that's the only cubed x we have in here, and then just plus 6 on the end. And that is our derivative. In today's video, we're going to be talking about the quotient rule, which is a strategy we can use to solve derivatives. If we would like to find the derivative of one function, f of x, being divided by a second function, g of x, we have to use the quotient rule, which is as follows. The quotient rule is g of x times f prime of x, which remember is just the derivative of our f function, aka our numerator, minus f of x times g prime of x divided by g of x squared. This is the quotient rule, and we can use this to solve any derivative where we have one function being divided by another. And we'll do 3 examples in today's video. Our first example will be we need to find the derivative of 3x divided by 7x squared. So first, let's establish what we're going to use as f of x and what we're going to use as g of x. And with the quotient rule, unlike the product rule, we do need to make sure that we have the right f of x and the correct g of x. The numerator will always be your f of x, so this one is f of x. And your denominator will always be g of x, so this one is g of x. 3x is f of x, and 7x squared is g of x. So now let's plug it into the quotient rule. So this is now equal to, put a big old division sign, g of x is just 7x squared, 7x squared. And we need to multiply that by f prime of x. In other words, we need to find the derivative of the numerator and then multiply that by 7x squared. Let's do that real quick over here in the top right corner. The derivative of 3x is just equal to 3. Using the power rule, we have a little invisible 1 here. We bring that to the front, multiply that by 3, and then subtract 1 here. What ends up happening is we multiply 3 by 1, which is just 3, and we take x to the 0th power, 1 minus 1 being 0, and anything to the 0th power is just 1. So the derivative is just 3. So we end up multiplying 7x squared by 3, and now we need to subtract f of x, which is just 3x, and then multiply that by g prime of x, which is the derivative of 7x squared. Let's find the derivative of 7x squared. Let's do that over here. d dx 7x squared. Once again, we can just use the power rule to solve this problem. Bring the 2 to the front, then subtract 1. So this is equal to 2 times 7x to the 2 minus 1 power. 2 minus 1 is just equal to 1. 2 times 7 is equal to 14. So this is equal to 14x, technically to the first power, but we don't have to write first power. Remember, anything to the first power is just itself, so we don't have to actually write the first power because it's implied. So then we just multiply 3x by 14x. And the bottom function is just whatever g of x is, in this case 7x squared, squared. So this is equal to 7x squared squared. Let's multiply all this stuff together and simplify where we can. So this then turns into 7x squared times 3. 7 times 3 is 21, and we just tack on the x squared. So 21x squared 3 times 14 is 42. X times x is just x squared. So minus 42x squared. And on the bottom, 7x squared times itself would be 7 times 7, which is 49. And x squared times x squared would be x to the 4th. Simplifying this down, 21 minus 42 is equal to negative 21. That's still x squared, of course, divided by 49x to the 4th. There's two things we can do to finish simplifying this equation. Technically, this is the derivative, but we can make it a little bit simpler. First of all, we can cancel out this x and remove 2 of the powers of x here. And we also have a common factor on top and bottom. Negative 21 and 49 can both be divided by 7. So we can just divide both of these by 7, along with canceling out this x squared. So the final answer to this, the derivative of 3x divided by 7x squared, is negative 3 divided by 7x squared. And that's our derivative. Now, as a little disclaimer, I wouldn't recommend using the quotient rule to solve this problem specifically, but since this is a lesson about quotient rule, we're going to use it in this case. The next two examples will be ones that you have to solve with quotient rule, don't worry. In our second example, we want to find the derivative of 3x plus 2 on top, 3x plus 2, divided by 6x plus 7. Once again, let's establish which one of these is f of x and which one is g of x. The numerator is always f of x. So 3x plus 2 is f of x, and 6x plus 7, the denominator, is g of x. Let's solve our equation from here. Once again, we just have to use the quotient rule to solve. So let's put a big old division sign here. First, we need to put in g of x, which is just 6x plus 7. And then we need to multiply that by f prime of x. So once again, we need to find the derivative of this function. We can do that over here. And just like in our last example, we need to multiply that g of x times f prime of x. So let's find f prime of x, in other words, the derivative of the numerator. And we can just do that down here. So the derivative of 3x plus 2 can be split by the addition sign. It's one of the properties of derivatives. So we can solve for each of these derivatives individually and then combine them to find our new derivative. The derivative of a constant, such as 2 here, is always 0, so this will just be 0. And the derivative of 3x, just like up there, is just 3. So 6x plus 7 times 3 is the first part of our equation. Now we need to subtract f of x, which is 3x plus 2, being multiplied by g prime of x. And we'll do that down here as well. The derivative of 6x plus 7, our denominator, can be solved the same way as this one. We can split these two by the addition sign, then find these derivatives individually, combine them to get the new derivative. So the derivative of a constant is still 0, and just like in this example and that example, the derivative of 6x is just 6. If you have a function that's just a variable with one coefficient attached to it and no powers, the derivative of that function will always just be whatever the coefficient is. So this is just 6. And then on the bottom, we just plug in g of x squared, which would be 6x plus 7 squared. We have a lot of simplifying to do, so let's continue doing that. In fact, I'm going to erase this so I have enough room. So 3 times 6x plus 7 is 6x times 3 plus 7 times 3. 6x times 3 is just equal to 18x. 7 times 3 is equal to 21. And now we have to subtract. 6 times 3x is equal to 18x minus 18x. And then we multiply 2 times 6, which is just 12. And then on bottom, we have, and remember, whenever you square something in parentheses, you don't just square 6x and 7. You multiply 6x plus 7 times 6x plus 7. So on bottom, we have 6x plus 7 times 6x plus 7. So on top, we can simplify some things. This 18x and 18x cancel out. 21 minus 12 is equal to 9. And since we have no x's in the numerator anymore, there's not really any reason to FOIL this all out. So we're just going to leave this as 6x plus 7 squared. So now we just have 9 divided by 6x plus 7 squared, and that is equal to the derivative. We're going to do one more example. Our last example will be finding the derivative of 3x minus 1 on top divided by x to the 4th plus 2. What is this derivative? Well, once again, let's establish what f of x and g of x are. F of x is always our numerator, so that would be 3x minus 1, and g of x is always our denominator, which is x to the 4th plus 2. Wow, I wrote that very poorly. Hold on. X to the 4th plus 2. They kind of got combined. I think that looks a little better. So let's plug that into our quotient rule formula. This is now equal to, big old division sign, g of x is just x to the 4th plus 2, So to find f prime of x, we just need to find the derivative of 3x minus 1. The derivative of 3x minus 1 is equal to 3, just like before. The derivative of a constant is just equal to 0. And the derivative of a coefficient multiplied by just x with no power is just the coefficient. So this is just 3. Now we just have to subtract f of x, which is 3x minus 1, and multiply that by the derivative of x to the fourth plus 2. Let's solve that down here real quick. The derivative of x to the fourth plus 2 can be split by addition. So let's find these separate derivatives and then combine them at the end. The derivative of a constant is just 0, so we don't have to worry about that. Using the power rule, we can find the derivative of x to the fourth is equal to 4, that's the power we brought to the front, times x to the 4 minus first power, which is equal to 4x cubed. So now we just multiply 3x minus 1 times 4x cubed, as so. And on bottom, we just have to plug in g of x squared. In this case, it's x to the fourth plus 2 squared. Let's FOIL out this function and see if we can cancel anything out. And I'm going to erase this here just so I have enough room. X to the fourth times 3 is equal to 3x to the fourth. 2 times 3 is just 6. Or 4x cubed times negative 3x is equal to negative 12x to the fourth. And 1 times 4x cubed is just equal to positive 4x cubed. Distributing the negative, negative times negative 1 is just 1 times 4x cubed is just 4x cubed. And then we're not going to FOIL this out on bottom because this is just going to look worse than in its simplified form here. So this is just x to the fourth plus 2 squared. Let's simplify the numerator to finish up our quotient rule derivative. There's only one thing to simplify. 3x to the fourth and negative 12x to the fourth can combine. So the final answer to this quotient rule problem is negative 9x to the fourth plus 4x cubed plus 6 divided by x to the fourth plus 2 squared. And that is the derivative of 3x minus 1 divided by x to the fourth plus 2 using the quotient rule to find it. In today's video, we're going to be talking about the chain rule, which is a strategy we can use to solve certain derivative problems. So the chain rule is a little bit weird compared to the other rules that we have for solving derivatives, such as the quotient, power, and product rule. Essentially, if we have a function, say, I don't know, square root of x plus 7, we can clearly define two distinct functions in here. We have x plus 7 as a function, but we also have this outer function here. This square root is also its own function. This function, of course, being the square root of x or whatever you want to put inside there. In this case, we have the variable x inside of a square root. So there's a very distinct outer function, right, outer, and also a very distinct inner function. So whenever we have a problem that looks something like this, we have to use the chain rule to solve that problem. The outer function will always be our f of x, and the inner function will always be our g of x. Knowing this, we can apply the chain rule to solve functions such as this. The chain rule is as follows. The derivative, d dx, of some function f of g of x, and this notation is just saying that we have a function within another one, such as what we have up here, f prime with g of x inserted into f prime times g of x, or g prime of x, sorry, g prime of x. This is the chain rule, and we're going to use this chain rule to solve some example problems because I'm going to be honest, this doesn't really help me much. Examples will help me a lot more. The chain rule is rewritten up here in case you want to reference it while we do the video. Let's do 4 examples so you can get the hang of the chain rule. Example number 1 will be the one that I showed here just a minute ago. We want to find the derivative of the square root of x plus 7. What is this derivative equal to? Well, let's establish 2 things. 1, we need to establish what the outer function is, and 2, we need to establish what the inner function is. And we talked about that just a minute ago. This little x plus 7 here is its own function, but it's also distinctly inside the function square root of x, as denoted as such. We have a very clear inner and outer function, so we know which will be our f of x and which will be our g of x when plugging into the chain rule. Let's write that down here. The outer function is the square root of x. And the inner function is x plus 7. Now, in order to use the chain rule, we need to both find f prime of x, in other words, the derivative of f of x, and g prime of x, also known as the derivative of g of x. So let's do that real quick so that way we can just plug them in. First of all, f prime of x, also known as the outer function, is the derivative of the square root of x. So how can we find the derivative of the square root of x? Let's do that up here. The derivative of the square root of x is the same thing as the derivative of x to the 1/2 power. Anything raised to the 1/2 power is the same as square rooting it, and we can use this to solve for this derivative. Using the power rule, which we learned in another lesson, linked up here if you'd like to learn more, tells us that we just need to bring down this coefficient, or this power to the front, and then subtract 1. So this derivative is equal to 1/2 x to the negative 1/2 power. So f prime of x is 1/2 x to the negative 1/2 power, which is also equal to 1 divided by 2 times the square root of x. This may look a little better to some of you, and yeah, it's a little bit less of a mess, so I'm going to use this. Now the derivative of x plus 7, also known as g prime of x, is equal to 1. And let me show you why it's equal to 1. Up here, we can solve it for x plus 7. We can split these two by the addition sign. That's one of the properties of derivatives that we learned in my video about properties of derivatives, which you can watch here if you'd like. And we can solve for each of these derivatives individually and then combine them at the end to find the derivative. One of the rules of derivatives is that a constant derivative is always equal to 0, so we don't even have to worry about that. And the derivative of x is just equal to 1. So the derivative of x plus 7 is just equal to 1, so g prime of x is just equal to 1. Now let's apply our chain rule. First we need to plug g of x into f prime. This is f prime, 1 divided by 2 times the square root of x. So this is equal to 1 divided by 2 times the square root, and we need to replace x with g of x. Our g of x was this x plus 7. So inside our little square root here, we just had to write x plus 7. And then, at the end, we need to multiply all of this by g prime of x, and g prime of x is just 1. So we can just multiply this all by 1. So our derivative is just equal to 1 divided by the 2 times the square root of x plus 7, because multiplying by 1 doesn't actually change anything. And that is the answer to the derivative of the square root of x plus 7. Now I will admit, this example you can solve much more easily without the chain rule, but I wanted to use this as an example because you could solve it with something other than the chain rule, and we're just getting warmed up. These next 3 examples require using the chain rule to solve. So let's do those now. Our second example will be finding the derivative, d divided by dx, of x squared plus 1 to the 3rd power. What is this derivative equal to? Let's talk about it. So once again, we need to establish an inner and outer function. And fortunately for us, this has a very distinct inner and outer function. The obvious one here is that x squared plus 1 is the inner function. It seems to be inside of this function, inside of the parentheses. The outer function might be a little bit trickier, but if you're curious what it is, it's actually this right here, this cubed. So let's write that down here. The outer function and the inner function. So we already established the inner function is x squared plus 1. We know that. But this outer function is a little bit trickier to find out. I told you that it's this cubed, and just like in the square root, it's simply just x cubed. If we were to plug in our inner function to our outer function, we would get this function. So that's basically what's going on here. Once again, we need to find f and g prime of x in order to plug that into the chain rule. So first, let's do f prime of x because it's pretty simple. F prime of x is equal to 3x squared. By the power rule, we take this 3 to the front and make it our new coefficient, and then subtract 1 from the power to get 3x squared. Our g prime of x, also known as our inner function's derivative, is also very simple. This constant, by the constant rule, will turn into 0. The derivative of a constant is always 0. And this x squared can be solved with the power rule. We bring our power to the front and turn it into a coefficient. So this turns into 2x, and then we subtract 1 from the power, 2 minus 1. So this derivative is just equal to 2x, and technically to the first power, but anything to the first power is just itself, so we don't need to write that. Now that we have everything, we can plug this all into the chain rule. So let's do that now. First, we need to write down f prime of x. This is 3. And then in parentheses, we need to put in g of x, which is x squared plus 1 down here. X squared plus 1. And that is all squared. As you can see, we replaced our x value in our f prime of x with the inner function x squared plus 1. And that's what we're doing here. And then we need to multiply g prime of x to this function here. So that's just 2x. This whole function is being multiplied by 2x. Simplifying this down, our final derivative by using the chain rule is equal to 6x times x squared plus 1 squared. And that is the derivative. Example number 3. We are trying to find the derivative with respect to theta Now, if you're wondering what's going on here, instead of writing d dx like usual, I wrote theta because we're doing this derivative with respect to a different variable, and in this case, it's going to be theta. The notation is just slightly different. It doesn't actually change the problem. Anyway, we're finding the derivative with respect to theta of sine 4 theta plus 2. What is this derivative equal to? So once again, we're going to want to establish our inner and outer function, and I feel like it's pretty clear in this example. We have a very clear inner and outer function, so we definitely need to use the chain rule. Inside of our sine function, we have 4 theta plus 2, and outside we have the function of sine, of course. So our outer function is equal to sine of theta, and our inner function is equal to 4 theta plus 2. Now, once again, we need to find the derivative of both the outer and inner function. This, of course, being f prime of x. The derivative of sine of theta is cosine of theta. That is one of the derivatives you really should memorize. It's a very simple one, of course, but you absolutely need to know this one. It's very important because it comes up a lot. And g prime of x, aka the derivative of the inner function, is equal to 4. The derivative of a constant is always 0, and by using the power rule, we have a power of 1 here. We bring that 1 to the front, then we subtract 1 from it, so we have 1 times 4 here, and then theta to the 0th power. Anything to the 0th power is just 1, so we just have 4 times 1, which is equal to 4. So that's why g prime of x is equal to 4. Now we just need to apply the chain rule. First of all, our f prime of x is equal to cosine. Inside that, we need to put g of x, which is this inner function here, which is just 4 theta plus 2. Oh, 4 theta plus 2 with a green parenthesis for consistency. And now we just have to multiply all of that by g prime of x, which is just equal to 4. And I could put times 4 over here, but I think it just looks nicer to write the 4 here as a coefficient. It would equal the same thing. So this is the derivative of sine 4 theta plus 2. We're going to do one more example for this video. For our last example, we want to find the derivative with respect to x, don't worry, we're going back to x like usual, of e to the negative x squared plus 3x. What is this derivative equal to? Now, I understand this probably looks a little intimidating, but it's not too hard, and we'll walk through it together. Once again, we need to establish an inner and outer function, and I think this is a little less clear than some of the examples we've done before. But remember, when we want to use chain rule, we're just looking for a function within another function. So as you can see, we have this x squared plus 3x within the function e to the x. So e to the x is our outer function, and our inner function is negative x squared plus 3x. Let's write that down here. Our outer function is equal to e to the x. And our inner function is equal to negative x squared plus 3x. Knowing this, we can now find the derivative of each of these and then plug it into the chain rule once again. First of all, f prime of x, in other words, the derivative of the outer function, is equal to the derivative of e to the x. And the derivative of e to the x is just e to the x. This derivative is probably the single easiest one to remember, and you should absolutely know it. It comes up quite often. Now, our inner function is going to be, well, kind of by default a little bit harder. So our g prime of x, aka the derivative of our inner function, is just equal to negative 2x plus 3. Both of these can be solved by the power rule. We bring this 2 down to the front, and that becomes our coefficient, and then we subtract 1 from this power. So then we get negative 2 times x to the first power, and remember, anything to the first power is just itself. So that turns into negative 2x. 3x is also solved using the power rule. We have a little invisible power of 1 here that we bring to the front. Remember, anything to the first power is itself, so we can put it there, but we don't have to. 3 times 1, of course, is just equal to 3, and then when we subtract 1 from this power, we get x to the 0th power. Anything to the 0th power is just equal to 1, so we get 3 times 1, which is just equal to 3. Now that we have everything, we can just plug it into the chain rule once again. This starts to get repetitive really fast. So our f prime of x is just e to the x. So we're going to put e here, but remember, we need to plug in g of x for wherever x is. So we just need to plug in this inner function back up there. So this is equal to e to the negative x squared plus 3x. And then we just need to multiply all of that by g prime of x, which is just down here, and that's equal to negative 2x plus 3. And this is the derivative of e to the negative x squared plus 3x. See, not so bad. Just kind of a repetitive rule that gets a lot easier with more practice. In today's lesson, we're going to be talking about higher order derivatives. The only difference between this and regular derivatives is that we do the derivative again. Let me explain that. Let's say we have the derivative x to the fifth. If we wanted to find the derivative of x to the fifth, we would just use the power rule. We take this to the front, subtract 1, so this equals 5x to the fourth. But it turns out that you can find more derivatives of this, or the second derivative, the third derivative, the fourth derivative, etc. This is known as the higher order derivatives. So in this example, if we wanted to find dx squared, which would be the second derivative of x to the fifth, we would first find the first derivative, which is 5x to the fourth, and then we would do the derivative again. We would find the derivative of this new function. So in this case, we would take this 4 to the front using the power rule. We take 4 to the front, then subtract 1 from our exponent. So this turns into 4 times 5 x to the 4 minus 1 power, which is then all equal to 20x to the third power. We can then do this again for the third, fourth, and fifth derivatives using the same process. Let's do some more examples so that way you get the idea, and we're going to do a couple common examples because there's some that are more useful than others. Oh, and something I want to mention, usually let's say we have f of x. If we wanted to note the derivative of this, we would write f prime of x. If we wanted to find the second, third, fourth, and so on order derivative, we can just denote that like this: f double prime of x, or f triple prime of x, and so on depending on what order you have. Pretty simple, just wanted to mention that because it's very useful notation. Okay, let's do another example. Let's find the third derivative, the third order derivative of sine of x. What is this equal to? Well, first, let's find the first derivative of sine of x. The derivative of sine of x is equal to cosine of x. This is one of those derivatives you really need to know and memorize. It's very important. It comes up very often. Now we need to find the derivative of this function. This will get us to our second order derivative. The derivative of cosine is negative sine of x. This rule is a little bit more useful whenever you do integrals, which is coming up in Calculus 1, but we're not there yet. And then we just need to find the derivative one more time to find the third order derivative. And the derivative of negative sine of x is negative cosine of x. By the way, this derivative goes on in an infinite loop. You'll never reach 0 like you would with some other derivatives. So the derivative of negative cosine of x is sine of x. And then, of course, we're just back to where we were before, and it goes in an infinite loop. Anyway, this is a very common example of a derivative you would find using higher order derivatives. And these derivatives come up a lot more in calculus too. Just figured you should know. Let's do another pretty easy example. In fact, this may be the easiest example we'll do. Let's find the third derivative of e to the x. So first we need to figure out what the derivative of e to the x is, and the derivative of e to the x is just e to the x. This is another rule that comes up very often and that you should know, and plus it's the easiest one to remember. I mean, come on, it's literally the same thing. To find the second order derivative, we need to find the derivative of e of x, and that's e to the x as well. And then to find the third order derivative, it's still e to the x. This is a really easy example because the derivative of e to the x is just e to the x, and you just do that over and over, but figured we should do it just for fun because it's so simple. Let's do one more simple example for this video. We're going to find the second derivative, so f double prime of x, of 12x to the fifth. We did a similar example at the beginning of this video. Let's just do another one. Let's first find the derivative of 12x to the fifth. Using the power rule, we take the 5 down to the front and then subtract 1. So this is equal to 5 times 12x to the 5 minus 1 power. 5 times 12 is 60 times x to the 5 minus 1 power, which is just 4. And then to find the second derivative, we do the same thing again. We pull this down to the front, then subtract 1 from the power using the power rule. So then this just turns into 4 times 60x to the 4 minus 1 power. 4 times 60 is 240. X to the 4 minus 1, which is third power. Like I said, this is a pretty simple example similar to the one we did at the very beginning of this lesson. In today's lesson, we're going to be talking about implicit differentiation. This differs from how we've been doing derivatives in the past, where we've had our derivatives expressed explicitly. For an example, let's just say we had the derivative of the square root of 1 minus x squared. The derivative of this problem is just equal to negative x divided by square root of 1 minus x squared. We could go through the whole process, but more importantly, I want you to see that we have a ddx equal to something. This ddx kind of acts like our y variable, and this is defined explicitly because y equals x. Now, the same problem could be defined implicitly as x squared plus y squared is equal to 1. If you were to give a student this problem and tell them to find dy dx, in other words, the derivative This would seem a lot more complex. How do we do that? We have this y variable here, which isn't the same as the x variable. How do we derive for that? And that's a good question, and that's what we're going to be solving today with implicit differentiation. Let's actually work this example out. So our example was x squared plus y squared is equal to 1, and we want to find dy dx. What is this equal to? Well, we can find most of this just by deriving normally like we've been doing in the past few lessons. So to start, we can just find the derivative of x squared. This is just power rule, so we bring this 2 down to the front and subtract 1 from the power. So this is 2x, and we can actually do the same thing for the y variable as well. We bring this 2 down to the front, subtract 1 from the power. So this is equal to 2y. But since we have a y variable here when we're trying to derive with respect to x, we have to tack on a dy dx. The reason we do that is because we're deriving for the y variable. And after all, we do need to find dy dx, not d dx. So we need to tack this on here. And this is equal to the derivative of 1, and the derivative of any constant is just 0. So now this problem is just a simple matter of isolating dy dx. And that's pretty easy. We've been doing this since Algebra 1. Here we just subtract 2x. So now this is equal to 2y dy dx is equal to negative 2x. In order to isolate for the dy dx, we just have to divide by 2y on both sides. So dy dx is now just equal to negative x divided by y. This negative 2 and 2 cancel out to just be negative 1, so that's why that's negative x over y and not negative 2x divided by 2y. And that is the derivative we were looking for. We found this derivative implicitly. In other words, we have two variables on one side instead of one variable defining the other. Remember, in an explicitly defined problem, d dx or f prime of x kind of acts like y. It's sort of the same thing, but in this case, we have the y variable within our problem. So that's the only difference here. We're only going to do one more example for this video, and then at the end I'm going to link another video with a lot more implicit differentiation examples because they're great and I don't want to just copy his video. So in this example, we need to find the derivative. X cubed plus y cubed is equal to 6xy. This is a little bit more complex, but mostly keeps the same strategies as before. So since we have the y variable within our equation, we do need to find dy dx. So let's find dy dx for both sides of this equation. Let's find it for both sides. Let's start with the left side. Just like before, we can just use the power rule to find the derivative of x cubed. So we bring our 3 down to the front times x. 3 minus 1 is 2, so our new power is 2. So the derivative is 3x squared. We do the same thing for y. We bring this 3 down to the front and subtract 1. So this is now 3y squared, but because there's a y variable here, we do have to multiply by dy dx. Now on the right side, we actually have to use the product rule. We have one function being multiplied by another, and because they're different variables, we have to use the product rule. Just as a refresher, the product rule is f prime of x times g of x plus f of x times g prime of x. So function number 1, or f of x, is going to be 6x, and function number 2, or g of x, will just be y. So first of all, f prime of x is just the derivative of our first function, which is 6x. The derivative of 6x is just 6, and now we need to multiply that by g of x, which is just y. So this turns into 6y. Now let's do the same thing, except we multiply by g prime of x. F of x is just 6 of x, so let's add 6x, and then multiply that by g prime of x, which is just y. The derivative of any variable that doesn't have a power on it is just whatever the coefficient is. And in this case, the coefficient of y is just 1. And since we just found the derivative of a function with the y variable in it, we need to multiply that by dy dx. So this is just 1 times dy dx. So I'm just going to write it as dy dx because 1 times dy dx is just dy dx. Once again, we just need to isolate for dy dx. So let's take the two functions that have dy dx in them and put them on the same side. So first let's subtract 6y. And in order to isolate for dy dx, we're just going to subtract 3y squared dy dx. So this problem now turns into 3x squared minus 6y is equal to negative 3y squared dy dx plus 6x dy dx. And now we have the variables isolated on their respective sides. But since these two do have a common factor of dy dx, I'm going to change this from this into dy dx times negative 3y squared plus 6x. We just factored out the dy dx and multiplied it within the parentheses instead. It's the same thing. And of course, to isolate for dy dx, we just had to divide all of this by negative 3y squared plus 6x. And we'll do the same thing on the other side. So dy dx now equals 3x squared minus 6y divided by negative 3y squared plus 6x. And that is the derivative of our implicitly derived function. In today's video, we're going to be talking about derivatives of trigonometric functions. In my past videos, I've used sine, cosine, and other trig functions in derivatives, but I realized I've never actually told you what these derivatives are. So in this video, we're going to go over all of those trigonometric functions. Starting off with the easiest one, which of course is the derivative of sine of x. The derivative of sine of x is just cosine of x. Very simple, very easy to remember. Just kind of goes from sine to cosine. Add a co to the beginning, you got the derivative. Now the derivative of cosine is a little bit different. The derivative of cosine of x is equal to negative sine of x. So they don't just flip-flop between each other, they also have a negative symbol in here. That trips people up sometimes, so be sure to remember that. The easiest way to remember it, in my opinion, is if you go from sine to cosine, you don't flip the sign. But if you go from cosine to sine, you do flip the sign. With the sign, of course, being positive and negative. And the other simple derivative is the derivative of tangent x. So the derivative of tangent is equal to secant squared, and then your variable, which in this case is x. Now the derivative of cosecant, denoted as CSC, as such, CSC of x, is equal to negative cosecant of x times cotangent of x. I will say some of these trigonometric derivatives are just kind of hard to remember and you just sort of have to memorize. But if you use them more in your examples, you get more used to it over time. Next for the derivative is secant of x. The derivative of secant x is secant x times tangent of x, as such. And the last derivative for our basic trigonometric functions is the derivative of cotangents. This derivative is equal to negative cosecant squared x. But we also need to go over the inverse version of all of these functions, so let's do that now. I'll write the inverse ones in red because they're like opposite or evil, I don't know. The derivative of inverse sine is equal to 1 divided by the square root of 1 minus x squared. The derivative of inverse cosine is equal to negative 1 divided by the square root of 1 minus x squared. Now inverse tangent is different than sine and cosine. So the derivative of inverse tangent, or tangent to the negative first x. By the way, this is not a power notation. A power notation would look something like this. Tangent of x to the negative first. This is inverse tangent. Don't get these two mixed up. Anyways, the derivative of inverse tangent is equal to 1 divided by 1 plus x squared. Definitely a little bit different than sine and cosine, but tangent is weird like that, so I guess it makes sense. All right, now time for the inverses of our cofunctions. The derivative of inverse cosecant of x is equal to, and I won't lie, these are hard to remember, negative 1 divided by the absolute value of x times the square root of x squared minus 1. Fortunately, secant follows a similar pattern to cosecant. And in fact, the derivative of inverse cosecant, sorry, I meant the derivative of secant is equal to, not cosecant, is equal to 1 divided by the absolute value of x times x squared minus 1. So the only difference between these two is that cosecant has a negative 1 and secant has a positive 1. And the last trigonometric derivative is, of course, cotangent. So the derivative of cotangent, or inverse cotangent, of x is equal to negative 1 divided by 1 plus x squared. Funnily enough, cotangent is the only one that mirrors its original function. We could go through and prove all of these, but we don't really need to. More importantly, you'll just need to know these for your next test. So now we're just going to do 3 examples. They're going to be really quick and easy of finding derivatives of trigonometric function. 2 of them are just going to be finding derivatives with trig functions in them, and 1 of them will use one of these functions in the problem. So let's do that now. I'm going to erase this, but leave all of these up here via screenshot. All right, example 1. Let's find the derivative of sine of 4x. Now, if you're not sure where to start, think back to some of the derivative rules we've done in the past. You may notice that we have an outer function and also an inner function, meaning we need to use the chain rule. And as a reminder, I'll write the chain rule up here. The chain rule, so d dx of f of g of x is equal to f prime g of x times g prime of x. So we'll use that in order to solve this. So first of all, what is f of x? Well, f of x is our outer function, which is sine. So f of x equals sine of x. And our inner function, which is 4x, will be our g of x. G of x is equal to 4x. Now we just need to find the primes, aka the derivatives of both of these functions. So f prime of x is equal to cosine of x. We just learned that one a minute ago. And g prime of x is equal to 4. Remember, if our x has a power of 1, aka no power, and it just has a coefficient attached to it, the derivative of that function is just the coefficient. Now that we know everything, we can plug that into our chain rule. So first, f prime is cosine of x. So this is cosine, and then inside we put our g of x function. Our g of x function is just 4x. And then we just multiply that by g prime of x, which is just 4. And this can just be rewritten as 4 cosine 4x. And that's our derivative. This one's not too difficult, but if you didn't know that the derivative of sine was cosine, you would have never figured out this problem. In our second example, we need to find the derivative of x cubed times tangent x. You may notice that this function is one function being multiplied by another function, meaning that we need to use the product rule. Just as a reminder, the product rule is equal to f prime of x times g of x plus f of x times g prime of x, aka the derivative of the first function times the second function plus the first function times the derivative of the second function. So let's do that here. So f of x is our first function. We can choose either one as f of x, but I'm going to choose x cubed because it's the first one I see. And g of x is just our other function, which in this case is tangent x. F prime of x, using the power rule, we take our 3 down to the front and subtract 1. So this is equal to 3 times x. 3 minus 1 is 2, so our derivative is 3x squared. G prime of x is equal to secant squared x. This is one of our trigonometric rules that we learned just a minute ago. So now that we have everything, we can just plug that into the product rule. F prime of x is 3x squared, and we multiply that by g of x, which is just tangent x. And then we need to add that to f of x, which is x cubed, times g prime of x, which is just secant squared x. And while this is the right answer, and you can leave it like that and you will have the right answer, we can technically simplify this just a little bit more. So what I'm going to do is factor out an x squared. We have an x squared here, we have an x cubed there, so we can factor out something from both of these functions. So this is now equal to x squared times 3 tangent x plus x secant squared of x. And that is the derivative, where once again, you wouldn't have been able to find the answer unless you knew the derivative of tangent x, aka one of the derivatives of our trigonometric function. We're going to do one more example, and it's going to be a little bit more confusing, but I'll walk you through it because it's actually not so bad. In our last example, we need to find the derivative of e to the arctangent x. Now, if you don't know what arctangent is, arctangent and inverse tangent are the same thing for our purposes. Arctangent is just another way to write inverse tangent or tangent -1 of x. I'll write that down over here. Arctangent is equal to tangent -1 of x. These are just different ways to write the same thing. And this is true of sine, cosine, and all the other trigonometric functions. So how do we solve this problem? Could we use power rule? Well, no, because this is a function and not a number. But we have a function, arctangent of x, within another function, which is e to the x. So we get to use the chain rule on this problem. First of all, our outer function, f of x, is equal to e to the x. Our inner function, g of x, is arctangent of x. Now let's find the derivative for both of these. The derivative, aka f prime of x, is equal to e to the x. The derivative of e to the x is just e to the x, the easiest one to remember by far. And the derivative of arctangent of x, if you remember from earlier, aka g prime of x, is equal to 1 divided by 1 plus x squared. So now we just need to apply the chain rule. First, we need to put g of x within f prime. F prime of x, which does not look like an f right now, f prime of x is equal to e to the x. So where we have x, we need to plug in our g of x function, which was arctangent of x. And then we need to multiply that by g prime of x, which is 1 divided by 1 plus x squared. And we could leave it like that. That is the correct answer. You'll get this answer right. But I'm just going to change it to make it look a little bit nicer. E arctangent of x divided by 1 plus x squared. Remember, when we multiply a fraction by something that isn't a fraction, technically there's a divided by 1 here. And when you multiply fractions, you just multiply top by top and bottom by bottom. So this is the same thing as e to the arctangent x divided by 1 plus x squared. And that is our derivative. In today's video, we're going to be talking about derivatives of logarithmic and exponential functions, because we have a few special derivatives for, well, logarithmic and exponential functions, just like trigonometric functions. Let's talk about them now. The first function we're going to talk about is by far the easiest derivative to remember. The derivative of e to the x is just equal to e to the x. Another very commonly used derivative, the derivative of ln of x, or natural log of x, is equal to 1 divided by x. This is another derivative that pops up very often and that you should just have memorized. Besides, it's not a terribly hard one to remember compared to some of the trig functions that we talked about last time, which if you haven't watched that video already, you can check it out here. Now for the slightly more complex derivatives. The derivative of a log function, such as log b to the u of x, with u being a constant, x being x, and b just being whatever base you're working with, this derivative is equal to 1 divided by u times natural log of b times du dx. Essentially, this rule is a very specific version of the chain rule, and if you don't know what the chain rule is, you can check out my video about it here. And the last derivative we're going to talk about in this video is the derivative of some function to the x power, or in this case, u to the x, because we might have a coefficient. This derivative is equal to a to the u times natural log of a, also multiplied by du dx. Just like with our log, this is essentially just a more specific version of the chain rule used for this function specifically. So now that we've established all of our logarithmic and exponential functions, let's do 2 examples today using these to solve these equations. I'm going to erase them from the board here, but I'll leave them up in a screenshot on screen. In our first example, we're going to find the derivative of cosecant 2 to the x. What does this derivative equal? Well, the first thing that's pretty evident with this problem is that we have a function within another function, so we need to use the chain rule to solve this problem. As a reminder, the chain rule, aka d dx of f of g, is equal to f prime with g of x inserted into it times g prime of x. We'll be using this equation to solve this derivative. Okay, first of all, what is f of x? Well, f of x is our outer function, and in this case that is cosecant. So cosecant x. G of x is our inner function, which is 2 to the x power. Now we need to find f prime and g prime of x. The derivative of cosecant x, which we discussed in my last video, which was about the derivatives of trigonometric function, is equal to negative cosecant of x times cotangent of x. And g prime of x is the derivative of 2 to the x. And the derivative of 2 to the x power, based on our exponential rule, is equal to 2 to the x times ln of 2, or natural log. I just say ln more frequently because it's just the shortened version. Now let's apply the chain rule to this problem. Our f prime is negative cosecant, and instead of putting x in here, we need to put g of x, which is 2 to the x, times cotangent of 2 to the x. Just like before, we have to replace our x in here with our g of x function. And then this whole function is multiplied by 2 to the x times natural log of 2. And that is our derivative, using the chain rule along with some exponential function rules. As you can see in calculus, we need to combine a bunch of rules in many problems in order to solve the problem more easily. Knowing your rules, such as log and exponential functions, the chain rule, and in this case especially the rules of trigonometric functions, is highly important, and I highly recommend you study and practice them quite a lot. We're going to do one more example for this video, so let's do that now. In our last example for this video, we need to find the derivative of log base 7 of square root of x. What is this derivative equal to? Now, this problem probably looks pretty intimidating at first, but based on the log rule that we just learned a minute ago, it's not quite as bad as it may seem. So first of all, once again, we have a function within another function, so we need to use the chain rule again. Oh, and I erased the chain rule from earlier, so I'm just going to rewrite it here real quick. Sorry about erasing it earlier, but I put it back here for your convenience. So in order to apply the chain rule, we need to establish our inner and outer function once again. Our inner function, of course, is going to be square root of x, and that will be our g of x, equal to square root of x. And our outer function, f of x, is equal to log base 7 of x. Now, once again, we need to find the primes, or the derivatives, of both these functions in order to plug it into the chain rule over here. So let's do that. The derivative of g of x, aka g prime of x, is the derivative of the square root of x. And remember, the square root of x can be rewritten as x to the 1/2 power. And this makes it much easier to solve because we can just use the power rule on this. So here we need to take this 1/2 to the front and then subtract 1 from our power. So this turns into 1/2 x to the negative 1/2 power. Now for the derivative of f of x, which is f prime of x, we need to find the derivative of log base 7 of x. And just a minute ago, we learned how we can find the derivative of a log function. And the derivative of any log function is equal to 1 divided by, in this case, x, because we have an x within our log, and then times the natural log of this little number right here, which is 7, aka the base we're in, which is base 7. Now we just need to apply the chain rule to this function and solve. So first of all, our f prime is equal to 1 divided by, and now for x we need to plug in g of x, so this is square root of x, times natural log of 7, and then we need to multiply that by g prime of x. So we need to multiply this by 1 divided by 2 square roots of x. Here's something fun about square roots. If we multiply the square root of something by itself, or in other words, a square root times the square root of the same thing, it just turns into whatever is under the square root. Oh, and I want to mention this just in case this was a bit of confusion for you. Here we have x to the negative 1/2 divided by 2. Anything to the negative exponent can be thrown into the denominator, and the 1/2 power is the same as the square root of x. So we move our x to the negative 1/2 to the bottom, so then it becomes x to the 1/2, which is the same as the square root of x, so we end up with the square root of x on the bottom. That is still being multiplied by 2 on the bottom, and 1 is being divided by both of those. So that's how we got there, just to clear that up. Anyways, back to what I was saying. Anything being multiplied by itself under a square root is just equal to whatever is under the square root. So this function is equal to 1 times 2x. Remember, square root of x times square root of x is just equal to x. And then this 2 is still here, times natural log of 7. And that is our derivative. That wasn't so bad, right? It was a little bit intimidating, I won't lie. Something like a log function just looks a little bit more funky than a normal algebra thing. But once you get the hang of it and get a couple practices in, it's not so bad at all. I hope you guys learned something in this lesson. If you did, consider subscribing. And also, if you want more Calculus 1 lessons, you can check out this entire playlist here of all of my Calc 1 lessons. I know, it's all in one convenient spot. It's awesome. I'll see you guys in the next video.